Today we have Dr. M. Marishwaran with us. He's an assistant professor in the Department of Biomedical Engineering at NIT Raipur. His areas of interest include experimental and orthopedic biomechanics, medical instrumentation, biosensors, and MEMS fabrication. Sir has completed his BTech from our very own institute, SSN College of Engineering, the Department of Biomedical Engineering. He has completed his MTech from BIT University and PhD from IIT Delhi in the field of experimental biomechanics. His postdoctoral work was on orthopedic biomechanics from IIT Madras. Dr. Marishwaran has also served as an assistant professor at Department of Sports Biomechanics at the Central University of Rajasthan. He has also served as a biomechanics engineer at the Indian Spinal Injuries Center, New Delhi, in the year 2019. He has more than 6 publications to his name since 2018. We welcome you, sir, to deliver your talk on estimation of forces acting on ACL during dynamic activities, a connect from characterization of human cadaveric knee ligaments to sports biomechanics. Over to you, sir.
Yeah, thank you. Thank you for the introduction. Let me start the talk. I hope my screen is visible.
Yes, sir.
Yeah. So I would like to thank SSN for inviting me for the FCP, for the Emerging Trends in Biomedical Engineering Research 4.0. Yeah. So this is the topic I have selected today is part of my PhD work and the work continued by my juniors in my PhD lab. So this is more on sports biomechanics and predicting the forces acting on the knee ligaments during dynamic activities. So already I have given a talk in SSN regarding my complete PhD work. So this will be a continuation of that talk. Yeah, I will touch upon the basics of that work also, so that the beginners can catch up, like who are listening to the talk first time, they can catch up what work has been done. So this work is predominantly experimental work, and then we have done some kind of computation for estimating the forces acting on the knee ligament. So we all know ACL, anterior cruciate ligament, is a soft tissue in the knee joint, which is prone to injury for the sports persons in most of the occasions. Okay, even irrespective of the country. Okay, this is the highly injured ligament, soft tissue in the knee joint. Okay, with irrespective of the sports, across the sports, you can see ACL is the highly injured knee ligament, and especially it is very high in soccer, where the running is actually more running and changing the directions. These kind of activities are more in soccer and kabaddi, these kind of sports. Okay. So our challenge was to understand the reason of failure, and then to study the characterization of the ligament at different rates of loading. So we came to a conclusion that, based on the literature, so ACL, anterior cruciate ligament, undergoes non-contact injury. So you need not go and hit your knee on an object. So that's a contact injury. Okay, you are not in contact with any other object or any other person, and still you can injure your ligament by running or just by a sudden acceleration or sudden deceleration activity. So that is called non-contact ACL injury. So we want to understand the mode of non-contact ACL injury. So we selected the rate of loading. Okay, that's also called strain rate. Okay, so that will take care of the deceleration and acceleration part. Sudden acceleration, sudden deceleration, which we generally do while we running. So this property we have chosen, and we have done some experiments on human cadaveric ACL by subjecting it to failure at different rate of loading. So in mechanical characterization, we call it strain rate. The rate of loading, we call it a strain rate. So we have characterized the human knee ligament at different strain rates, and from the data available, we were able to use an existing model to predict the forces acting on the ligament during different rate of loading. From that, we were able to predict the forces which may act on the ACL during dynamic activity. So you can see the ACL will go a little bit into the anatomy and little bit into the mode of failure, how the failure happens in an ACL. Okay, the being inside the synovial joint, ACL is not able to regenerate itself after an injury unless an MCL, which is outside the knee synovial cavity, it has the option of regenerating itself. It can do a clot formation and collagen production and healing, which can happen in an MCL, but in an ACL, there is the tear which is happening in the ACL does not have a chance to repair on its own because it is already in a synovial bath, which doesn't allow the clot formation to happen. Okay, and also there's a link between the ligament injury to the osteoarthritis. Okay, there is the cartilage degradation which is happening in the knee joint. So whoever has undergone ACL injury, even if it is treated or untreated, eventually he will end up getting osteoarthritis. So in the slide, you can see the slide. On the left side, you can see a knee joint. The femur has a degraded cartilage. So this is an osteoarthritis condition. There is a relationship between these two, and the biochemistry is also so much exciting. It says that there are some markers released in the blood, which is an indication of collagen problem in the collagen metabolism. So when the collagen metabolism is destabilized, you have the problem in the degradation of the cartilage. So this event is triggered by the ACL injury. There is a separate study which says that just by a blood test you can say whether a ACL is injured or not. You don't need to do a imaging study, X-ray or a CT scan or an MRI scan to find out whether ACL is injured. Just by doing a blood test, you can find some markers in the blood which they say that ACL has been injured. And again, the replacement tissue for ACL, which is the patellar tendon, so that is also another soft tissue in the knee joint, but you can see the mechanical property of the ACL and the patellar tendon. It is not made for each other. Patellar tendon is not supposed to replace ACL, but we are doing it happily in the surgical room. Why? Because it is stronger than ACL, but it is stiffer than ACL. We don't need to replace ACL with a stiffer material, but that's what surgeons are doing. And the other options, Achilles tendon, semitendinous graft, they are also not strong enough. Patellar tendon is strong enough, but it is more stiffer than ACL. Okay, it is not like replacement for the ACL. Then these are the different methods of analysis of non-contact ACL injury. Okay, and whatever is highlighted in yellow, that's what I have done in my work. So I have done experimental characterization of cadaveric samples, and then we have also developed a musculoskeletal model, and we have done some mathematical analysis to predict the forces acting on the ACL. We can also do a video analysis. We can ask a questionnaire to the athlete. We can do some image-based analysis, okay, X-ray, CT, or MRI understanding, and also we can do some study on the live subjects, okay, through invasive methods, through implanted sensors. But again, that is very tedious given the permissions required. And again, we have other computational aspects like finite element methods. Okay, so again, how ACL is undergoing an injury, I will explain a little bit of the mechanism. Then I will go into my experimental work. So ACL generally it undergoes injury when you are doing a lateral compression. Okay, so lateral compression, and then there is a valgus loading on the knee joint. Okay, so when there is an ACL lateral compression, the MCL is also taut, the ACL is also taut. Okay, and then the lateral compression is followed by internal rotation of the tibia. Okay, the internal rotation of the tibia, that one triggers the failure of the ACL. Okay, so once the ACL has undergone failure, the opposite happens. There's an external rotation of tibia followed by posterior translation of the medial femur. Okay, so this is what happens during the ACL injury process, and this is a study which was interesting. This is an old study that was in 1970s, 80s. So what they have done, they have taken a cadaveric knee and they have put a sensor within the ligament. Okay, they have attached the sensor to the ligament and they are simulating some movement. Okay, in the experimental condition on the isolated cadaveric knee. So they simulated some knee angles, which is similar to walking, and they measured the forces acting on the ligament through the sensor. Okay, so this is the only study which is available which says what is the force acting on the ligament during walking and other activities. Okay, so ideally it is a isolated knee sample in which the low S sensor was attached. It was not a walking data, but they simulated the walking movement by just adjusting the knee joint through different angles. But again, the ground reaction force and the body weight are not considered because it's an isolated sample. Okay, they have also applied some torque. Okay, and they have done some applied some moment, and they have found they have seen what is the forces they have measured and reported the forces acting on ACL. Ideally, this should be our target, but this study has a problem. There is no ground reaction force. There is no effect of body weight. It is just an isolated knee sample in which people have put the sensor and they have simulated the knee angle, which is equivalent to walking, and they have reported the data. So as far as this data, you can say 300 Newton is the highest force acting on the ACL ligament. And then during some moment, internal torque and varus moment, you can see the various forces. Like 250, 300 is the maximum force Newton acting on the knee ligament, which is still doubtful whether this low force will be acting on the ligament. So that was this is the starting point of our research. So we want to obtain this data, okay, for a real subject who is working for a live subject who is working at different speeds, who is running at different speeds, and who is able to do some complicated sports activities like plant and cut. A plant and cut is what something like sudden change in the direction of running. The sports person keeps on running, and this is done often in soccer and other games like kabaddi. Okay, suddenly they plant their foot and they change the direction. That's called plant and cut. So these activities we want to estimate the forces acting on the ligament. So how we go about it? So initially we took the human cadaveric knee sample, and then so we name it FATC. It's the femur ACL tibia complex. Okay, so that was tested over a range of strain rates just to simulate the dynamic loading, how the behavior, force elongation behavior of the ligament during the dynamic loading processes. That to understand that we did the cadaveric study, and from the force elongation data, we took an existing equation which was relating the forces acting on the ACL with the strain rate of the ligament.
ఇవాళ మీటింగ్ ఉందని వచ్చిందా?
Yeah. So this is followed by the musculoskeletal model which we have developed in OpenSim. So we incorporated this equations and the parameters to estimate the forces acting in the ACL during dynamic activity. So this is the flow of the work which I will be focusing in this presentation. So to start with, we wanted to do a tensile characterization of femur ACL tibia complex, so which I will call it FATC. So these are the different methods of holding a knee sample with ACL in between. So we remove all the other tissues so that only ACL is being studied. And again, ACL is a very small tissue. It is only 30 mm long, 3 centimeter long. Okay, it is very difficult to hold it. It is a very soft, slippery structure. Okay, so these are the different methods reported in the literature how to clamp the sample before doing a tensile study. So we have from this literature we and also little bit of understanding about how the ligament fails. So we developed our own gripping method. So before that, yeah, I also tested isolated. This is an isolated ligament. Okay, so this is an isolated ligament, and this is the force elongation behavior for an isolated behavior ligament. So we had faced a lot of issues in gripping the sample, and the sample always slips. Okay, and also we cannot appreciate all the modes of failure. So the ligament is not something which always fails in the middle. It's called midsection failure. There is also an insertion failure. The ligament remains intact, but it pulls away from the femoral insertion point. Okay, that's called insertion failure. So we also have femoral insertion failure, tibial insertion failure. So to appreciate those things also, it is better to test the sample as a whole. Okay, with the femoral insertion region, tibial insertion region, with a part of the femur, with a part of the tibia. Okay, so you can see the loading setup which we have used for our experiment. Okay, so this is the and also we did some finite element study on what happens to the if you use a normal gripping available with a UTM, conventional UTM. So we went for we stopped using the conventional gripper, which gave the slipping of the sample was unavoidable when we use the conventional gripper. But at the same time, we need to apply a tensile load. So we developed a cylindrical gripper in which the slipping of the sample is avoided. Okay, and this is how we dissected the new sample. And then the sample is loaded in the UTM for the tensile characterization. So we tested the sample at different strain rate, at rate of loading, which was possible in the available machine to us. Okay, and we also faced some issues. So if the bone is osteoporotic, as you see, so the tibial end is an osteoporotic bone. So what happens is when you apply a tensile force, the rod will cut through the sample because the bone is weaker. Instead of transmitting the force to the ligament is not the weaker structure. The bone becomes the weaker structure, and it takes the load and it undergoes. It doesn't help. It doesn't lead us to load the bone, load the ligament, and we end up loading the bone instead of the ligament. So it will be a challenge, not challenge. It will be impossible to test the osteoporotic sample using this method because the bone is not strong enough to undergo the forces which is applied by the gripping method, and it will cut through the bone. So these are all the experimental problems which we have faced. And coming back to the data, so what after the experiment, after at different strain rate, we got the force elongation data. The force elongation data, which is at different strain rate. So we wanted to use that in an existing equation. There's a DeVita and Slaughter model, which is relating the collagen fibril strain rate loading of the collagen fibril present in the ligament. But again, this model doesn't take care of the contribution of the matrix and other fibers, which are also components of the ligament. Okay, so, but we still this is the only available equation which was there already. The left hand side is the stress acting on the ligament, and the right hand side you have a lot of parameters, K, eta, alpha, and beta, and eta dot is the strain rate. Okay, so finally, we were able to relate the stress acting on the ligament with the strain rate with the help of these four parameters. So the next step was to estimate the values of these four parameters using the experimental data, which we have done at different strain rates, which we have done, and we have obtained the parameters value. So I'm skipping this part where we are focusing on the forces, the pure experimental study of the cadaveric tissue. If you want, I can explain it later, but I may deviate from the actual topic. So this is just what forces acting on the different strain rate, the failure force, and why the failure forces are behaving in this way at different strain rates. Okay, so if anybody is interested, yeah, I can come back to this point. So coming back to this parameter estimation. Okay, so we have the d beta equation and we have the force elongation data for force free strain rates. So we have tested at 0.003 per second, 0.03 per second, and 0.3 per second, which is nothing but 5 mm per minute, 50 mm per minute, 500 mm per minute. That is the travel of the crosshead. So that is the rate of loading or the rate of displacement you are subjecting the ligament or FATC unit. So that we are converting into strain rate. So you are getting the simple per second. From mm per minute, you are getting per second. So this is the three different strain rates which we have tested, and using this experimental data, I think we have tested 8 samples, and from the 8 sample average data, we are obtaining the alpha, beta, k, and eta values, so which will fit the experimental data with the d beta equations for the parameter. Okay, so you can see the simulated data based on the using the equations, d beta equations and the parameter. 0.003 and 0.03, there is not much difference between the force elongation behavior. And 0.3 per second, you can see a jump in the graph. So you can find a higher failure force, and the failure elongation is or the elongation is practically lesser than the other two strain rates. So we validated our model. Okay, and also we validated at a different strain rate which we never tested. So we tested. So the data was only of these 3 strain rates, and we did an experiment on a different strain rate, and just to compare the ability of the model to predict at any strain rate. We need not predict at only these 3 strain rates. In between any other value also we want to predict it. We chose a value of 0.1 per second, and then we did an experiment, and then we studied the simulated data, and then we were able to see how good our model is able to match the experimental force elongation behavior. Then we developed a knee model on an OpenSim platform. So this is a freeware. Okay, you can and you can also add modules to this freeware. This is actually a musculoskeletal model based on rigid body dynamics. This is not a finite element model. Okay, finite element model is the actual model. You will get the actual solution, but the problem is it is computationally heavier. Okay. And then that is also not freeware. Okay. So this one we can also easily incorporate the motion data. So if you have a gate lab and if you want to incorporate the ground reaction force, kinematics, this you can give those motion files as input to the OpenSim, and you can study the model in the OpenSim platform. So that is the advantage of using OpenSim, so which we finally ended up using to predict the forces acting during dynamic activity. So we took an existing model and we started adding more components to the existing model. Okay, so we added the meniscofemoral ligament, patellar femoral ligament, fibular ligament, transverse ligament. These components were added to the already available 18 bundle model. So we created a 25 bundle model. So you can see the green lines are the ligaments or the soft tissues which are connecting between 2 anatomical regions. So when you use an OpenSim, you should be very specific. You should be anatomically very clear where the ligament is originating, where the ligament is ending, and in the process where it can rub over a bone, it can go around a bone also. Okay, so these things you should declare very clearly for the model to capture the behavior. Okay, so we again, ACL is not one tissue. There are 2 bundles within one ACL tissue. So this called anterior bundle and anteromedial bundle and posterolateral bundle. Okay, depending on the direction of the orientation. So we call it AACL and PACL. Okay, so there are other tissues also, capsular ligament and other patellar ligaments, which we have added to the model. And then we also introduced a term differential interbundular strain. Okay, it will because the two bundles are within the same sheath. So when you take a ligament which is having more than one component, for example, the patellar tendon, you can see three components. There are three. It has three bundles. Okay, patellar tendon is a bigger tissue, so only that it is used as a reconstruction material for ACL. Okay, so it is made of three tissues. So once you have more than one component, one bundle within a tissue, so there is a sliding of the bundles also happens. So this sliding activity also will create a shear, which we wanted to address in differential interbundular strain. Okay, so we have developed some equations for predicting the differential interbundular strain, and then we simulated the knee, some kinematics. So such kinematics like flexion, some rotation, internal, external rotation, abduction, and adduction, and then we studied what is the strain happening on the ligament. This is very straightforward. Okay, you have a model, you move a component of the model, so the ligament is attached to two landmarks. The distance between the landmarks change during the movement. So the strain is reported as a function of the knee rotation angle or knee flexion angle. Okay, so this is straightforward in OpenSim, which will give us the strain. But we are interested in measuring the stress, measuring the force acting on the ligament during the activity. So this is also a important finding, but we are more than the strain. We are interested in the stress. Okay, so we will again take this d beta equation, and then we obtain the parameters, and then we add it as a plugin to the OpenSim software. Okay, and this is the plugin. You can see, so you can we have fed in the alpha beta k value, and then we are able to find the stress acting on the ligament for different rate of loading. Okay, so this was one contribution to OpenSim. We have given all the plugins online. You can download it and start working on it, and you can also add your own contribution. So this was developed by some research group in Stanford, I think 2005, and people have added a lot in the OpenSim musculoskeletal model, and any group can pick up at any point and they can continue working on it. So coming back to, so till now we are able to predict the stress for different rates of loading. So now what we are interested is to predict, to simulate some dynamic activities like walking, running, plant and cut. Okay, and then just study the stress, monitor the stress acting on the ligament, monitor the forces acting on the ACL. Okay, so we all know this is the gait during walking. Okay, and this is the gait during running. Okay, so you don't have the double limb unsupported phase, which comes only during running. We don't have that during walking. So remaining all things are little bit common for the running gait and walking gait. Okay, and then you have the. So I'm introducing you to the plant and cut activity, which we have simulated in the OpenSim model. So plant and cut is nothing but you are running and suddenly changing the direction and you are moving in another direction. So you have an approach and you do a plant and cut, you have a takeoff. So approach is you are approaching a point, a particular point with an approach velocity, and then you are doing a plant and cut. You are planting your foot, in this case it's the right foot. You are planting the right foot and then you are changing the direction, that's called takeoff. You are cutting it and you are taking off, so the velocity decreases and then again it increases. So we name it takeoff. Okay, so these are the components Was there any?
Sir?
Yeah. So I thought somebody want to ask anything.
No, no, sir.
So yeah, this is the plant and cut activity. Again, plant and cut, we were simulating with a flexed knee and with an extended knee. Okay, so you can, this is the second case where the person is doing a plant and cut with an extended knee, and here the person is doing a plant and cut with a flexed knee. Okay, and also we uh, tried different approach speed, different takeoff speed, different plant and cut knee angles. Okay, so these things we simulated in OpenSim. Okay, and then we were able to calculate the stresses acting on the ACL. Okay, ideally we should take the ground reaction force. Okay, from the ground reaction force in a gate lab, and the kinematics, we have to estimate the forces acting on the ACL. But again, this plant and cut running is a highly risky activity which will injure the ligament. Okay, we cannot. That is the beauty of the simulation. Sometimes we cannot do some experiments where we are going to do any harm to the subject. Okay, it's a destructive testing. But again, it is not a polymer or something you can destroy. It is a human tissue and is a live subject. We cannot force a person to do a high risk activity knowing that it will injure his ligament, or there is a high chance of getting his ligament injured. So we created this entire approach, plant and cut, takeoff and running. This event we created it in OpenSim as a motion file. Ideally, we should have, so we can take a running data, we can take a walking data from a gate lab, feed it into the OpenSim, and then we can get out the using our model, we can get out the forces acting on the ACL. Okay, but again, this is a high risk activity, so we didn't do this actual data acquisition in the gate lab. We had a normal walking data, and which we had fed into the OpenSim, and we got the forces acting on the ligament. Okay, but again, we cannot do this for a high risk activity. Okay, and this is the walking data which we have taken from a reference. We also had our own walking data in the GATE lab, but for understanding and comparing the results, we took this walking data. So they, based on the stride length and the stride time, they are calculating the speed of the walking. So they are classifying fast walking, normal walking, and slow walking. Okay, and then this is coming to our plant and cut, which has different cases like approach, plant and cut.
Sir, your voice. Hello, sir. We are not able to see your slide, sir. Your sir.
Sir, can you try now? Can you unmute yourself? Sir, still your voice is not audible.
Sir, you're on mute, sir. Sir, now can you unmute, sir?
Sir, now, can you try now?
Is it audible now?
Yes, sir.
Yes, sir.
I think there is an issue with my headset. Let me restart it. Is my screen visible?
Yes, sir.
But my voice is not getting
You're
clear.
audible, sir.
Audible, but I'm using the system mic rather than my headset mic. Just give me a second. Hello, am I audible?
Yes, sir. You're audible, sir.
Okay, I think it is. So can you tell me which slide was
All this is
there
done, sir.
when I
This is done.
this is done? This is
Yes,
done.
sir. Yes, yes.
This is also done.
Yes, sir.
I think this
Yes,
was
sir.
the slide.
Yes, yes.
Okay, so we had selected from the literature some different walking speed, okay, based on the stride length, stride time, and then we simulated the event in OpenSim, and we were predicting we were calculating. It is not predicting. Okay, we are calculating the forces acting on the ACL, and then for plant and cut also, we had different approach speed, different takeoff speed, and then different angle of plant and cut. So we simulated these activities, okay, by varying these parameters, by varying different approach speed, by varying different takeoff speed, by changing the angle of the knee during plant and cut. So these data we took from the literature and we made our own motion file, okay, and then we got the forces acting on the ACL using our OpenSim plugin. Okay, so we all know we can get the strain easily. From the strain, we calculated the instantaneous strain rate, from which we again using our d beta equation, we calculated the force acting on the ligament. Actually, the equation gives us the stress. From the stress, we got the force, and what is reported here is force, that is the Newton per kilogram body weight. Okay, so you can see for different activities like walking, running, flexed knee, plant and cut with a flexed knee, plant and cut with an extended knee. You can see the different strain rate, instantaneous strain rate, and then forces acting. I think the 40 Newton per kilogram body weight, that is the maximum forces acting on the ligament on the ACL. So this is the absolute values. Okay, this is absolute single point value, maximum force. And also we studied the continuous variation of the data during different phases of the activity. Okay, this is the plant and cut. So I will come with walking. So walking at different speeds. Okay, we compared with other models also. Okay, there's other models by other research groups. So they didn't include the strain rate in their model. So you can see the force acting on the ligament is almost same for different walking speed. Okay, fast, normal, and slow walking speed. So these are the model used by Zhu et al. And Smith et al., which is the OpenSim knee model used for predicting the forces acting on the ACL. Unfortunately, they didn't include include anything for the strain rate. So they are not able to. All their predictions are overlapping. So what this data says, the force is same if you walk fast, if you walk slow, if you walk normal, which is difficult to believe. Okay, so this is for our developed class. Okay, non-linear strain rate ligament class. Okay, so you can see there is a difference in the for the fast, slow, and normal, if not very big difference, but there is a differences in the actual values of the forces for different speed of walking. Okay, the orange one is the fast walking. You can see the orange one is having the highest force always. Okay, and then this is for the plant and cut activity. Okay, so when you do a plant and cut activity, okay, so what is the forces? So again, plant and cut has an approach phase, plant and cut phase, it has a takeoff phase. So during the different phase, what is the continuously where the forces acting on the ACL is continuously varying. Okay, so the dotted one and the dashed ones, okay, the continuous ones are the one which is without the for the flexed knee, and the dashed one is for the extended knee. Okay, the dotted ones are for the extended knee, and the continuous line is for the flexed knee. So that is for different, the green, purple, and red for the different speed of approach. Okay, you can see that difference in the forces acting on the ligament, which is predicted or calculated by the OpenSim model. Okay, the maximum values we have reported in this table for different activities like walking, running, flexed knee, and an extended knee. Okay, and how it is behaving dynamically during an activity is given by this graph. Okay, so this is the contribution of our work. So we can predict the forces acting on the ACL during a dynamic activity without actually doing the dynamic activity. Okay, so the target was to match the data which match something like this. So this was a walking data, but this was done on a cadaveric study with the loads, with the sensor put inside the ligament. Okay, but again, the ground reaction force and the body weight were not considered, and we know they do play a role. Just by horizontally keeping isolated knee and simulating different kinematics, different knee angles, we cannot say what is the force acting on the ACL. But that is what is they have done at and they have published this. And yeah, so I will stop here and I'm open for questions. I would also thank my collaborators. So these are the publications arising out of this work, and I acknowledge my authors and other collaborators, okay, faculty and staff of my department at IIT Delhi, then our collaborators from AIIMS, my colleagues, friends, and family. So I'm open for question. Am I audible? Hello?
Yes, sir, you're audible. Participants, you have any questions?
So any biomechanics simulation guys are there? Or all are image processing, signal processing guys?
कोई टेंशन नहीं, सेकंड हाफ में दे देना 2-3 बजे 2 बजे मैं आपको एक्सपेरिमेंट करूंगा भैया.
Sir, actually there is a question in the chat. What are the emerging in biomechanics?
See,
Let go.
the mostly sports biomechanics is one of the very emerging field. In India, we are giving more importance to sports. Recently, you can see a lot of injuries happening every now and then. So the concept of sports biomechanics is to improve the performance and reduce the chance of injury. Okay, even my presentation. So I took a dynamic activity I took a tissue which will get injured often, and I took a dynamic activity which will result in the injury of the particular tissue. Okay, so these things are more thrust areas in sports biomechanics. Okay, and also you can also look for some haptics in surgical training. The orthopedic surgery, again, it is done on cadaveric samples, how they train. So you can work on some haptics to train the surgeons. Okay, how they are able to feel the. You can look into some models. You can develop some models. You can suggest some materials which are replacement for human bone, not for surgical replacement, but for surgical training. Okay, so there are some material from the material side. You can suggest some materials which is good for surgical training, and also for you can also develop some instrumentation related to that. Okay, so again there is EMG signal processing always. You can do fatigue prediction. Okay, how to reduce the fatigue. Okay, those kind of work also we can do in EMG signal processing. Also create. Let me see question one by one. How to correlate muscle forces and features. Can you be very specific? What features? It is more of the from the EMG signal processing aspects you are asking, or related to my talk? Okay, signal features. Okay, so I'm not that much expert in signal processing, but again, you can look at some time domain features. Okay, you can look at some time domain features, and then you can actually ideally we do a normalization. Okay, every muscle is different. My muscle will give a different force than to your muscle. Ideally, we normalize with respect to the body weight, or we have a normalized value. Okay, so that normalized value is compared with the with at different conditions. If you want to predict the onset of fatigue, okay, if you want to predict the muscle, if there's a rehabilitation work, okay, you want to strengthen a weakened muscle. Okay, you have a weak muscle and you are developing a protocol to strengthen the weakened muscle. So you have to monitor the force on the muscle at different time points. Okay, you are developing a routine. For example, you are giving a task to the patient. The patient is doing the task at different timeline. What is the forces? Normalized force, again, it is not absolute force. Normalized force the patient is able to exert. Okay, so with respect to different time points, we can measure the normalized force, and we can say whether there is an effect of the protocol which you are suggesting. Okay, so that is thing which comes to my mind. Again, frequency is also there. Frequency of firing. Okay, but again, based on the rehabilitation work I have seen, they focus on the normalized force values at different time points, to see whether the muscle is actually responding to the protocol. Okay, and also you can take some frequency domain parameters also. Any more questions? You can ask directly. Yeah.
Yes, sir. This is Vijay. Actually, I have a question. Do we have any wearables or any kind of shoe kind of stuff to measure the various parameters related to the muscle, so that we can?
No, you can get plantar pressure. Yeah, you please complete
Yeah.
the question.
Yeah. So that the maybe the food falling or any kind of food drops can be analyzed. That kind
I
of
have done little bit of that work. I thought of presenting that only, but I'm lazy to prepare that presentation. So when I was in Rajasthan, so we were trying to study the different landing heel strike. Okay, you can landing foot strike patterns like heel strike, mid foot strike, and toe strike. You have different running style and how to relate it with the fatigue. Okay, so there we did an image processing study. We didn't do any signal processing study. The idea, so what you are asking is there are some plantar pressure insoles which you can put it inside the shoe. So it will map the forces acting on the sole. Okay, from that you have to transmit to the forces in the calf muscles.
Yeah,
Okay, I was
think
trying to
you're telling about
if
pressure
you don't have a
mapping.
gate lab,
Yeah.
yeah, exactly. If you don't have a gate lab, if you have a gate lab, you will get a ground reaction force.
Yes.
From the ground reaction force, you have the kinematics. From the kinematics and ground reaction force, it's an inverse problem. You can go towards what is the force generated, or force acting in the muscle, or force acting on the ligament. That is what my approach was about. But again, if you don't have a gate lab, you can buy some insole, or you can make your own. I can share you some papers.
Yes, custom
Okay,
made
there are
or
some,
tailor made.
yeah, you can put some
insoles.
sensors along the space, different locations in the sole, and attach it, put it below the shoe, and do a wireless transmission, and acquire the data and process it while you do a dynamic activity. So that is the force acting on the sole, on the foot. It is a plantar pressure. We call it plantar pressure.
Yes. Yes.
Okay. From there you can start. But again, kinematics without video analysis, because we need both. Only kinetics will not solve the problem.
Yeah, got it.
Okay, you need to have some kind of video, even if can be a 2D video analysis. Okay, to get the kinematics, and then from the kinematics and kinetics, you can predict you can compute the forces acting on the forces generated by the, see, if you have a wireless EMG machine, wireless EMG data acquisition system, put it in the calf muscle, you have a plantar force measuring setup, put it in the under the shoe, within the shoe, make this person run, collect the data. Here, okay, but again, we may not have everything with us.
Okay, but to set the gate lab, we need a huge investment. So
you can without, but at least wireless EMG.
Yeah. That is possible.
Wireless EMG,
yeah.
I think it is like 7-10 lakhs. You can get a wireless EMG setup, and this plantar pressure setup is very. You can make it custom made. There are some research grade plantar insoles available, but you can make some custom made sole also to monitor the plantar pressure. And once if you have wireless EMG, then most of the problems you need not worry about the kinetics. You can focus fully on the kinetics.
Yes.
But again, no gate lab, no wireless EMG, then
yeah. Yeah, got it. Yeah, thank you. Thanks for your reply, sir.
Any other questions?
I think there are no questions. Nirma ma'am. Okay, I think there are no questions from the participants. So thanks for your acceptance, Dr. Marishwaran from NIT Raipur. and sure, very soon we will collaborate, and we expect your support in all the ways. Thank you for your invitation and your presentation.
Thank you, and I wish my connection with the SSN will continue, and we will do some collaborative works, our student exchange, some kind of activities, and we will stay in touch. Thank you.
Yeah, sure. Thank you, sir. Thank you. So, dear participants, your next session will start by 1 o'clock. So the session will be, the presentation will be given by Mr. Srinivasa Raja from Phoenix Medical Systems, Chennai. And the title of the presentation is Medical Device Standards, Patient Safety and Risk Management. Please join in the same link by 1 o'clock. Thank you all.